Hello everyone, my name is Jim, and today we're going to be answering your Fusion 360 questions. Feel free to submit questions using the link in the chat or at the bottom of your screen, and I'll start working through them in the order that we receive them. Let's see if we've got anything to start with for today. Alright, so it looks like we do have a question from John, who wants to know how we can take a picture of a part and make it the proper size. Okay. So Fusion 360 allows you to import a canvas, and then you can use that canvas to trace on top of to copy in a part that you can't always get the proper CAD model from the manufacturer for. The challenge is that with these pictures, there's no way to know if they're the proper scale or not. Traditionally, what you would do is put a ruler in the image as well, and then draw a sketch on top of it with a line, and then just play with the scaling of the image until the ruler lined up with the lines that you made in your sketch. However, I'm going to show you guys an easier way of doing this. So I've got an image here of a part that I'm going to be using for an upcoming project, and what I can do is insert that as a canvas. And we can see it is there on the base. We hit OK. Now this is not the right size. If I were to create a sketch on top of this right now, we can see this whole part is only about 1/4 of an inch by 1/2 an inch. But if I pull up the data sheet for the part that we are designing here, you can see it's actually supposed to be about 166 millimeters across. Now sometimes these data sheets will give you all the numbers you need, but in this specific example, you can see it doesn't give me much information related to the mounting holes that should be present here and here. And a lot of the numbers are going to have to be building off of each other, so it's a lot better to just start with this. Now, the one important thing we're going to note here is this dimension right here, 112 millimeters. That is the dimension given for the PCB backplate of this large 7-segment driver. Let's move that back over here. And if we get out of this sketch, rotate our view to match the sheet, you can see this is a top-down image of the part. You can see those screw holes I was talking about that aren't present. What we could do is go into our Canvas folder in the browser, right-click on the image, and then hit the Calibrate button. What Calibrate allows us to do is select 2 points on the image and input a distance value between them, and then we can use that distance value to automatically scale the entire canvas. So what I'll do is I'll zoom in, and I'll try to select the very edge of the PCB, and the very edge of the PCB. And then I will input 112 millimeters, like it says in the data sheet. And now this has been scaled up automatically to the right size for us. Now if we create a sketch on the top, let's verify to see if it's the right size. So this part should measure 48 millimeters. And it looks like it is slightly off, but it's close enough for what we're trying to do. The canvas approach is not always ideal for when you're trying to get very accurate measurements. Especially with a very large part like this, you can see due to the perspective of the camera, some of these are not head-on to the camera. So we're going to have some bowing and some skewed values as you get further and further away from the center of the image. However, the key thing that I wanted was just the position of these 3 holes, and this should get us close enough that I'll be able to achieve that pretty easily. So I can just make a circle there, and a circle there. Obviously, they're not going to perfectly line up, nor did I model them to be an exact match. I'm going to have to use some other manufacturing or assembly method to get these to line up perfectly. For me, what I'm planning on doing is using an oversized hole and an undersized bolt, and then I can bolt it from either side with a nut and a washer, and it'll provide enough friction force to just hold it in place correctly. Once that's done, I can then just go through, give myself a rough idea of the shape of the part. And that's enough for me to start modeling and getting something roughly into the design. All right, let's save that. And let's see if there's any more questions to answer yet. All right, no new questions as of yet. Remember to submit those questions at the link in the chat or at the bottom of your screen. In the meantime, how would I open up one of my other projects and I'll just work through my normal daily workflow and you guys can watch and sort of get an idea for how I work. Let me turn off the screen recording for a second while I do that. This is a high-powered rocket that I designed, and I'm planning on launching sometime in August or September. One of the things on my to-do list is to go through and reorganize the avionics bay and make it a lot better. So while we wait for new questions, let's just go through what's wrong with that right now. So this is a very complex, large, multi-part assembly, so I'm going to start by hiding everything we don't need, such as the charge canister, the sustainer, and the booster, leaving us only with the avionics bay. You can see in here I have a mix of a few different parts. I have some parts like this that are either manufacturer representations of a real part or something from GrabCAD. And I have these just boxes, essentially, that represent other parts that there were not easy or accurate CAD models to access. Right now, all of these are hanging on a very large, complex assembly of 3D printed plastic that's not very easy to work with. So we're going to go in and try to clean that up. Let's start by hiding even more of this stuff that we don't need. For those of you that don't know, you can hide parts by double-clicking the component to activate the entire component, then hitting the eyeball next to it in your browser. You can also right-click on the part and hit Show Hide. It's either or, whatever works best for your workflow. If you just click once and then try to right-click, you'll only be selecting the face, so it won't give you the option to then go in and hide it. With components, if you double-click, it'll select it. And let's Show Hide. Alright, so this is currently set up for a flight configuration with a lot of cameras and a lot of other stuff that we don't really need. So let's start getting rid of these. You can see I made a subcomponent that contains multiple other components that houses all of the cameras and Raspberry Pis to make them easier to access and edit. I can just select that subcomponent, hit delete, and it removes them all. If you were setting up for multiple different operations or multiple different configurations of the same CAD model, it might be preferable to just hide those, and then if you need them later, you can re-show them. Since those are gone, we also will not need any of our mounts for the Pis, so we can get rid of those. And we're going to redo all the mounting in here anyway, so let's just show all the printed parts and get rid of them. And I don't believe we'll be doing any live video, so let's get rid of the transmitter and the antenna that you normally would use for those. So now we have just a few parts floating in space. The only way that we have to constrain these is this central threaded rod that runs through the entire length of the body, and we have the exterior tube that they all need to fit inside of. At either end, we have aluminum caps. We can drill and tap holes into the bottom cap, but not the top one, since it seals the chamber. So what is the best way to arrange all of these and then get them all connected up cleanly and easily? Let's start by giving ourselves as much space as possible. So that is a flight board, that is a switch, and that is a tracker. So to start with, we need a second one of these. And I'm just going to jump in and change the units to inches, make it a bit easier to work in. A lot of my older designs I used metric, so they were all in millimeters. And we got a new question. Hold on. It's a new question from Alex, who wants to know what/how is generative design? Alright, so that's a good question. Let me save out of this and let me jump into one of my generative design projects and we can go over what it is and how it works. Alright, so here I have an example of a generative design part. Let's go through and take a look at what it is and how I arrived at this shape. So for those of you who don't know, generative design is a technique that you can give the computer a set of some basic information and a load case, such as a force, and then it will go through and design the optimal part for your application. This is a 2-position vice handle that I had the computer generate to be able to sustain a load of 250 pounds plus a factor of safety on the handle, which will be threaded into this hole here, when I'm clamping on the vise using one of these 2 hexes. Let's go into the generative design workspace and take a look at what I did to get this result. Hold on a second. This open the wrong file. Let's open this one. So this is what the computer started with when I told it I wanted to generate this vise. Each of these colors means something different here. The red is keep out or obstacle geometry. This tells the computer that it cannot generate any geometry inside of where those shapes are. So you can see here I use that to make the hole where the handle will thread into, as well as the 2 shapes for the hexes. Below that, it's a bit hard to see. Let me hide these bodies. There we go. This piece here is what I told Fusion that I'm starting with. You don't have to give generative design a starting point to work from, but it does help a lot and it will reduce the total computation time significantly. You could also see I had a couple of pieces here that were green. What green means that this is part of the design that I want Fusion to keep. In this example, I gave it just a cylinder with enough space to thread and to hold on to those 2 hex pieces. Anything outside of that green that's not in the red, it's now able to modify freely to make the best possible design. The stock here is just another starting shape that I gave it. What'll happen with this is it won't make any part larger than this starting shape, so I already had a piece of material in mind to make this wrench out of. So let's hide that. And let's take a look at how this actually works. This is a good example of a multi-part study, since if you think about it, if I'm applying force on this handle, I need to be able to be safe and effective to use and not bend or deform or break when the vise is on this point or the vise is on this point, the low torque or high torque hexes. You achieve that by, inside of the study, setting up multiple different load cases. So if we take a look at study number 1 here, and I activate it, study number 1, I had a low torque operation, which would be that I'm applying 250 pounds here, and this hex is constrained, and I had a high torque, under which this would be where the load is applied, and this is where it's constrained. When you have multiple load cases inside of a single study, it will take all of them into account when it's making the part. Once you have a study set up, you can start the study by just hitting the generate button. It will take cloud credits if you have a personal or commercial license. I believe educational licenses come with an unlimited number of free cloud credits, so you can experiment with it as much as you want. If we go into the Explore, this is the wrong file. We go into Explore here. Nope. My setups with all these are a little bit of a mess, so you'll have to bear with me for a second here. You know what, here's actually something good to talk about. This was one of the first attempts I made at making this vise. Now you can notice this is obviously a lot more intricate and complex as compared to this one. The difference is that when I made this one, I didn't give it any constraints on manufacturing. I told it that we can create this part out of aluminum in any geometry that it could possibly think of. Obviously, machining something like this would be nearly impossible. So, for the next couple, I told it to constrain itself to using only plate stock and cutting it in 2 dimensions. This also allows you to then define a tool. So, if you notice, all the internal radii of these pockets are big enough that I can easily get an 1/8 inch tool inside of them. If you don't check that, sometimes it'll make pockets that have a 1/64 inch radius, which is nearly impossible to actually manufacture. Let me open up another example of generative design that I just finished, and we can walk through how the computer iterates through all of these. This is the setup for a payload Sabo that will fly in a high-powered rocket later on next year. This is a fairly simple setup. All we had is these top and bottom pieces that I wanted to keep the same. We had to cut a hole all the way through the length of the part to tie some shock cord off to the Sabo so it doesn't fly out of the rocket. And the only other constraints that we have for the obstacle geometry are the exterior of the tube and the payload that needs to fit inside of it. If I open up the Explore menu here, it'll give us an idea of how the computer worked through this problem. So if we take a look, this is the part that it ended up coming up with. It's a fairly simple part, made out of ABS plastic. But you can see over here it has a 6.08 factor of safety compared to the load cases that I gave it. So it's already a very strong part for our needs. This is also useful if you're doing a lot of parts. This will give you a ballpark estimate of the manufacturing costs and time and what tooling would be needed. Since this will be 3D printed as a one-off, we don't very much care about these, but it is good info to have. So you can see down here at the bottom, this is iteration number 46 of this design. So when the computer first got this part, the first thing it did was just connect everything together with a large body. Now this would work fine, obviously. It is way above the minimum factor of safety, but you can see its mass is almost 3 pounds. We told the computer to optimize this design for weight reduction. So what it's then going to do is look at where there is low stress on the body. Wherever there's low stress, it knows that it could make that part thinner, and then it can remove material, make the whole thing lighter, and get closer to its goal. So it will then begin to iterate, making some parts slightly smaller and smaller and smaller. You can see this edge here through the multiple iterations is getting thinner and thinner. If we then continue forward a few iterations, you can see now it's starting to open up a slit in the middle. We're still way above our minimum factor of safety. That slit becomes larger. Now in generation number 14, it's starting to thin out the material in the center of each of these parts now. By iteration 18, that slot has connected all the way through. It's getting deeper and deeper. We're getting closer and closer to our desired factor of safety while still reducing the mass. If we jump ahead, you can see those features are becoming more pronounced. This part here is becoming thinner and thinner as we go. You know, if we were to jump back now to iteration 1, you could really see the difference. As this part gets thinner, I'm not sure how clearly it comes across, but some of this blue is actually starting to turn to green. Green is the ideal stress level it wants. You can see a little bit of green in here. Not much at the top. Tiny bits under there. If we jump forward another 8 generations, the parts become even thinner. Our factor of safety is lowering. And our weight, we started to remember at about 2.7 pounds. Now we're down to 0.46 pounds. And it's going to continue to remove material in this slot here. So we jump back to 46. You can see here, this is really the part where it would fail if we continue to make it thinner. This is clearly green, so the stresses are already approaching the factor of safety there. But we've been able to reduce a part that we originally had at about 3 pounds down to only 0.369. So it's an incredible weight savings, and it didn't take any work on my part. I set this up, and then I went for lunch and came back an hour or two later, and it was all done. If I'm happy with this one, I can then just create a design or a mesh from it, and that will give me the finished part with a parametric history that I can then go in and edit as if it was a normal parasolid. If you had multiple studies running of the same part, they would all show up here. And then you can go through and sort them. So let's say that you wanted a part that was only $200 or less. You could set filters. If you were trying multiple different manufacturing methods, you can go in there and modify those to only view the ones that you want. It can even sort them by visual similarity. And like I said, all it took to actually set this up was a couple of very basic bodies and then a rough idea of what the forces on these two parts would be. And the computer did everything else for me automatically. Let's see if there's any more questions. Remember, guys, you can submit your questions at the link in the chat or the link that you see at the bottom of the video. All right, no new questions yet. Let's jump back into another project and take a look around at some of the other things that Fusion can do. Oh, I know, actually. I had a lot of questions about manufacturing in Fusion and how you could use it to get surface finishes. let me open up one of my previous projects with CAM. We can review CAM a little bit. This is a remove before flight safety arming housing that will fly on a rocket and allow us to remotely arm and disarm the rocket from the outside. Let's go through how I would manufacture this part. So before we start, let's just take some rough dimensions of the part to give you an idea of what we're working with. It can sometimes be a bit deceptive when you're in CAD how large or small a part actually is. So if I use the measure tool, and measure this, we can see the entire part is just under an inch tall. From end to end, it's under 3 inches. And from side to side, it is under a ½ inch. So a very small part we're working with here. You know, these holes here, for instance, these are, I believe, just an M2 thread, so very small parts we're working with here. Small parts are good from a manufacturing cost standpoint. You know, for materials, this is a very cheap piece of stock I can go out and buy for maybe $5. The downside is that when you get into small tools, they get exponentially more expensive. So you want to try and use as large of a tool as possible wherever you can on this part, which obviously will be difficult since there's so many small features. Let's go into the manufacturing tab and walk through the CAM workflow for this part. Let me enable the model. There we go. So the first thing I did is I bought an aluminum bar and I roughed out blanks. So if we edit one of these setups, you can see the piece of stock is 3 by 1.5 inches by a ½ inch. This is just a piece of 3 inch by 1.5 inch bar that I bought. It was about 2 feet of, and then I just cut it down with a bandsaw to about 0.55, 0.6 inches, and then faced them all off with a shell mill to get the final shape. Now, some people would say maybe let's start by holding this upright, drilling all the holes in the top. Maybe we do the entire exterior perimeter first, something like that. But what you really want to start with, actually, are these 4 very small holes here. Which, it's 8 holes in the final design, but when this is a solid block of metal, it is just one continuous hole that ends up being 2 later on. So why is that? The pre-drill for an M2 thread is 1.5 millimeters, or something like that. It's an incredibly delicate drill. And drills, especially small drills, don't like it when they're drilling and then meet an open pocket of air and then go into the material again. A lot of times this would cause the drill to deflect and snap. That's why when you pre-drill a hole, you use a starting drill that's very stubby and strong to get the hole started that you can then get the main drill in there. So the first thing we'd go in and do is drill with our starting drill the starting holes, and then go in with our actual drill and using a very light peck cycle so the chips don't break, so the chips break rather than the tool break. It will work its way through the material. Nice and slow and steady. We don't need to rush this. You know, we'd rather have a good part than a broken tool. So now that that's done, again in the same idea, we want to drill holes first before we start cutting into them. We're going to cut this long hole down the entire length. Now, in addition to reducing the chance of breaking our drill with an interrupted cut, this will also be good when we go in to cut this top feature. we're going to have to go on there with a very small end mill that's not very good at evacuating chips. So what we can do is start this operation by drilling all the way down on either side, and then all the chips and coolant will flow into this hole and just out the side of the part rather than gumming up our tools. So let's look at how we did this one. See, the first thing we do is we go in with our tiny spot drill just to get the hole started. Then we go all the way through and down to the bottom and out the back using a 5/16 drill. Now the final hole dimension isn't 5/16, it's 3/8 if I remember correctly. We want to start with a 5/16 though, since we want. They're not good though at getting a nice finish on the inside of the part. This is also an application where you might use a reamer, for example. But I have a long end mill, not a long reamer, so that's the route we're going to take. So you can see the next operation that it would do is it would take this very long end mill and just lightly spiral it all the way down and through the part. If we look at it from the underside, that's what it would look like. And then the last thing it's going to do is do an even smaller spiral, because if you notice there's a step between these two diameters to stop the pin from just flying out the back of the part. Let's just see. Alright. So if we were to simulate that now, let's start by simulating the first setup. So we're going to go through, drill those holes. Then we're going to come up here. You can see we start by spot drill. And this is a much bigger drill than the 1.5 millimeter drill we used before, so we can take much deeper pecking cycles. You can probably hear my computer spooling up in the background. Simulating CAM is very difficult for Fusion 360 to do effectively, so it will eat away at your graphics card pretty quickly. So you can see once we finish drilling the hole, we're going to come in with that long end mill and then start spiraling our way down. We're not taking a very aggressive depth of cut, and we're also not going down deep then doing a contour like you normally would, because this tool is incredibly fragile. Since it's so long, you normally want to take, I believe it's a 3% width of cut, versus normally you might see a 15 to 40 or even 60%. Now what we're doing is taking a skim pass. It's doing the same operation twice, and the idea is that any deflection in the tool, since this is such a long tool, would cause the part to be slightly out of dimension. The skim pass just goes through and cuts out anywhere that it deflected earlier on. Then it can retract all the way out, plunge all the way in, and cut the bottom. Now you can notice the actual features for this hole don't go all the way through the stock, but I drilled through all the way to start with. Similar to what we were talking about before, this gives a path for all the coolant and chips to fall out of the part while we're machining. So a bit of a spoiler here you can see on the side, but the next thing we would do is the top and sides of the part. So at this point, we would grab the part on this excess stock that's down here at the bottom, and then this would allow us to machine the entire outside contour and top and inside pockets of this part all at once. Normally you want to machine dimensions that are relative to each other all at the same time. Normally that means critical dimensions such as 2 bolt holes that need to go into the same part should be machined at once. In this case though, we're talking about the surface finish of the outside of this part. If I were to machine down to about here, then flip the part, and then machine to here again, there's a chance that those two sides will be mismatched when I come back up. So you want to try and cut all that at once if possible. So we take a look at that. First thing we do is we come in with the big end mill and we rough out all the stock on the top. Then we come in with a fly cutter, which Fusion doesn't do a very good job of representing, but it will allow us to get a very smooth finish on the top. Then we're going to come in with an end mill rather than a drill, bore out those holes to final dimension, and then there are those coolant drain holes I mentioned. And looks like we have a question from Donna. Let's see what Donna has to say, and then we can come back to this in a minute. So Donna says, "Hi, I'd like to learn how to make connectors for jewelry. The jewelry is about 30 millimeters in size. Is 30 millimeters too small?" Well, that's certainly not too small, Donna. Connectors for jewelry, it depends what kind of connector you're talking about specifically. If you're talking about just a clasp, like a magnetic clasp, that's something that you can easily design with small magnets and a bit of super glue. Generally, though, a part like that is something that you would see purchased from a jewelry supplier for making your own jewelry. And while we're at it, let's just check to see if there's any other questions that I missed while we're working. Oh, okay. Hopefully that answered your question for you, Donna. If you have more information or you want to send in a rough idea of what you're thinking about, we could take a look at it and offer some suggestions on how you can make it easier to manufacture or design. But till we get that, let's get back to this. So we were just talking about boring these holes. A nice feature in the Fusion 360 cam is you can see I have these threaded holes here. I didn't model the threads, I just applied the threads as a face. When you go into cam and you select a threaded hole like this, it will automatically drill it or bore it out to the pre-threading dimensions of the hole. So this is a, if I remember correctly, an M5 hole. So it'll probably bore it out to closer to 4.3, 4.4 millimeters. Same with this other M5 hole, and this one's a 1/4 to hold a, what do you call that, a ball detent. Just pre-made from McMaster-Carr. It's a great component. It's threaded on the outside, and then it just has a spring-loaded ball detent out the bottom. So what we could do is thread it in there, and then that'll allow us to retain the pin for this arming mechanism when it's not in use. So in addition to those 3 holes, like I said, we're going to drill, or bore rather, holes down into this pocket so that when we come back through and machine this pocket with a normal contour or adaptive operation, we have somewhere for all the chips and coolant to flow out of. So they'll flow down through those holes and then just out the side of this hole and down into the machine tray to be recycled. So you see then going with the bore is just going to, a pocket. The pocket's going to slowly ramp down all the way through the part until it comes out down at the bottom. Then we come in with a really big tool that gives us a lot more stick out and a lot better depth of cut. Allows us to come in and finish up everything here, or rough it out rather, in 2 passes. And finish it in 2 passes. If we had spares of that extra long end mill to play around with, it would be nice to finish this all in 1 pass at 1 depth of cut, but I don't think the flutes on that one are quite long enough. So I'd rather use this 3/8 inch Lakeshore Carbide tool that I know can stand up to the cutting forces more than well enough. And once that's done, I'll just come back in again with a chamfer bit, put a chamfer around the outside edge, and I'll probably want to come back in as well and chamfer the tops of these holes and slots. But let's take a look at what that would look like. If I start from the top, go through that operation, and start here. To the best of my knowledge, Fusion doesn't have a way to start a simulation partway through the list of operations. I know you can simulate, say, just a single operation halfway through the setup, but I don't think there's a way to start there necessarily. So you have to start from the top, hit the fast forward button until you get to where you want to be, and then just hit play. So let's turn off the model, and let's see what we're going to do. So I think just 1 too much. So now we're going to come in with that 3/8 tool, like I said. You can see I'm starting with cutting barely anything. I'm not 100% confident in the dimensions of the stock, so I start with a very light depth of cut. That way, if the stock is actually bigger than expected, I'll be just taking it down to the proper size then and there. You then see I'm coming in and cleaning it up just with a facing operation back and forth. Something like an adaptive might have been a bit more efficient here, but this is fine, really. It's not always about the best efficiency. I've found that the facing operation can be a bit more reliable, and it gives much better chip evacuation than the adaptive does when you're trying to do a face like this. So you can see this tool, obviously this one's not a very good representation. This is actually the Tormach Superfly, or what it would look like in CAM. Let me see if I've got a picture of that for those of you who might not be familiar with the Superfly. Here we go. So this is what the Tormach Superfly actually looks like. It's just a single spinning insert that's extended out and off to the side of the shank. It gives really great surface finishes, but since it's so precariously off balance like this, you can only take a very light depth of cut, and even then it's a little bit scary. Now Fusion, obviously, it's not worth the time and hassle of going through and modeling what that looks like, especially when it's just going to be spinning at a couple thousand RPM. So Fusion just models what the silhouette of it would look like if it's spinning for a long amount of time. So you can see if we zoom in very close, we're taking just a tiny, tiny depth of cut there. But it's worth it because it gives us a almost mirror-like finish on the top of aluminum. So you can see now we're coming in with that 1/8 inch end mill, and we're going to start going through and doing all of our boring operations. You could pre-drill these. I don't have an automatic tool changer on my machine though, so every time that I have to switch out multiple drill sizes, it does get a little bit annoying. So I like to do as much as possible just using a single tool. So you can see it automatically calculates what's the pre-thread size for all those holes, and we'll drill them out accordingly. And it's going to cut those down until we are coming into the slot below it, or the hole below it. Like that. Now we'll come in and finish up this slot here that'll actually hold the electronics for the arming mechanism. We're doing a very slow ramp down. This will unevenly wear the tool. The tips of the flutes will wear out faster than the rest of the tool, which means we will have to throw it out before its full service life. However, we're using I believe it's a Speed Tiger is the brand. It's an 1/8 inch end mill you can get a 5-pack of for 10 or 20 bucks on Amazon, so premature tool wear is not the end of the world for this kind of tool. Now, if this was something like my Lakeshore Carbide engraving tool that already has a very short life on it, it's an expensive tool and it doesn't take much to break it, I would want to go for a bit of a safer, more conservative tool path that'll evenly wear the entire tool. So you see it's just going to continue to go down. Let's get a view from the front of the part so we can see the progress that the tool is making. If we speed that up a bit, it's going to keep going down and down. I could probably remove that partial retract that it does every time. If I'm making a lot of these, those saved seconds will count up over time. Eventually though, it's going to break through the bottom. All the chips and anything that were in there are going to fall out and be cleared out nice and easy. And now we got our really big 3/8 inch Lakeshore Carbide tool, and we're going to go around and cut the entire outside. So you can see here, it can take a very heavy depth of cut. I might actually have to go back in and double check that, but I can push this tool to 50, 60 thou depth of cut, or width of cut at full flute depth with no problems whatsoever. The worst part about doing that is that you end up just getting pelted with these shards of aluminum that go in every direction at high speeds. And what's crazy is that this is only a finishing end mill from Lakeshore. So I'm really curious to see what a roughing end mill from them would do. So you can see now we're going to step down a little bit, cut a bit more. Keep in mind that while we're doing this, we'll be holding on to it with the vise right in this area that's still green. Oh. There we go. Simulation bugged out for a second. Then we're going to go around the entire side. We're going to just take a finishing cut. You can see it's a very light cut, only 10 thou on the width. That ensures that there's no spring back in the tool, and we'll get a nice clean surface finish. Then we'll come with the chamfer tool, give it a nice chamfer along the top. It's not necessary, but it does look very nice, so there we go. So now, what's the next operation that I'm doing here? Ah, I see. So the parts that will go into that slot at the top are micro limit switches. Like from the manufacturer, they have a lot of variance in their final dimensions for the package. They're not really meant to be mounted in a constrained area like this. So what I did is I made a second operation here. Between these, there'd be a full stop. And what happened is I'd come in with the micro limit switches that will be put into this housing, and I will try and fit them in and see how good of a fit it is. And if it's a good fit, then we're fine. If it feels like it's a bit tight, I have a series of contours here that I can modify the cutter compensation to slowly open up this pocket until the micro limit switches will fit. You could avoid this by using a better dimensioned micro limit switch. The challenge is I bought these switches, I think it was 20 of them for $5, versus a better dimensioned one might be 10, 20, 30 bucks per switch. So in the grand scheme of things, my time is not worth a lot. I'd rather spend the extra time slowly tuning these in to fit rather than spending the money to get the good parts. So let's turn off transparency and it'll make it a bit easier to see. So that just went in, and if you didn't see it, it went in and just barely took a shave off of everything there. And then once I know that those dimensions are good, it'll come in and do the contours. Since if we cut the contour, then walked out the dimension more, it wouldn't be a very good chamfer. And there's the part, at least, the top half of it. Now we just need to separate it from the stock underneath. There's no real critical dimensions in the bottom of this part, but I do want to engrave some information on the bottom for people to use in the future. So what I would do now is flip the part 180 degrees and use this flat face and this flat face as our XY datum in the vise. Once it's flipped, I'll take that 3/8 inch Lakeshore tool and I'll go over and face the top just like we did before. Start with the rough face, then we go in with the finishing after that, again using the Tormach Superfly. Now here, just like before, you could have used an adaptive, but I specifically chose a facing operation here for a reason. You see how when we're at our final depth, the material that's left to remove sort of sticks out over the side? Sometimes when you're doing an adaptive, it messes up and gets confused, and it will cut, leaving a massive chunk of metal just sort of floating freely in the air, which is very dangerous. You know, it can break off and it can fly towards the operator, it can get lodged under the tool and cause the tool to break. So going with a face, while technically less efficient for tool wear and time, it does ensure that we clean that up exactly how I want it to. And then same as before, we have that very inaccurately modeled Superfly coming in, taking just a tiny amount off the top. Then we'll come with the chamfer tool, put a nice chamfer around the whole side, nothing too crazy. Again, not necessary for proper operation, but it does look nice. And then we come in with my favorite tool. This is the Lakeshore Carbide 20 thou ball engraving tool. It gives beautiful engravings on parts that can be very intricate, very small, and really, it is probably one of my more expensive, quote-unquote, tools that I've bought. But for what it does, it's pretty affordable. I think it's a two-sided tool that was about $25. So, really, if you use it right, it's going to last forever. And you can see we can get very small engravings. Keep in mind, this entire part is less than a 1/2 inch across. and we were able to get that detailed of a letter. The tool pathing for engraving doesn't really make much sense as you watch it through. It will do like half a letter, jump somewhere else, it'll go and start doing a bit of text at another line, only to then jump back and keep doing what it's doing. I'm sure the computer has it figured out and it knows what it's doing, but it looks weird when you're watching it. So you can see we just go through, we engrave the university name, the group name, what event it's going to be used for, and my name and the serial number. And then we can engrave the logo of the team right there. This tool, it's a bit hard to see from the simulator, but it actually comes down to a 20 thou ball at the bottom. It doesn't come down like a traditional V-bit to an infinite point. This makes it really great at removing material very quickly and giving a smooth, clean finish to the bottom of your engravings. So what I could do with these once I'm done is I could take like a bit of black nail polish or a black acrylic paint, squirt a bit onto this part, and then scrape it in with a squeegee. And it gives a really nice finish to the part. Since it's such a clean pocket that the tool left, it's very receptive to the paint. And that's all there is to making this part. Once that's done, I'd be able to just undo the vise, pull it out. Might need to use a bit of Scotch-Brite to clean up the vise marks on that finished face, but other than that, we're all set. Oh, we've got a... Let's see. We've got another question from Donna. I've created a file that's about 30 millimeters. I'd like to create another file that will attach to the first, but no glue or connectors. Seems like 30 millimeters is too small for hinges and a 4 millimeter nozzle. What do you think? So, 3D printing hinges, it is true that the larger the hinge is, the easier it will be to print. You might want to check, usually a 4 millimeter nozzle refers to 0.4 millimeter, so you might get a lot better resolution than you're thinking of. 30 millimeters is probably okay. What I would suggest is instead of trying to design these yourself, I would use an OpenSCAD hinge generator. So let me pull this up real quick. For those of you who don't know, OpenSCAD is a mesh editing software similar to... it's a CAD package like Fusion. It's not at all similar to Fusion. It allows you to define a mesh based on a series of mathematical equations, and you can do some really complex things with it. So if we go to Thingiverse.com, which is the website that hosts a lot of pre-made 3D printing designs, you can see there's a ton of different hinge files, and if we sort for customizable, which is the OpenSCAD variants, we can see that there are some hinge designs that you can just 3D print, like these, parametric hinges. So what you could do is if you wanted a specific hinge and you didn't want to design it yourself, you can open it in the customizer and then just go through and input the dimensions you want, and it will make you a single piece print in place hinge for your needs. So while we wait for more questions, how about we take a look at how you would set up the cam for engraving something like this. Because there's a lot of things that I learned designing this part that hopefully I can teach to you guys, and you can skip trying to get stuck on some other more complex things in the future. So if we go into the design for this, all this engraving is sketches. And now if you notice the text here, there's something special about it. So let me edit the sketch that this is on. Sketch 22. So normally when you make text on the top of a part, you go to create text, click a spot, and then write down whatever you want it to be. Like that. Then I hit OK. So you can see that text, it has thickness to it. If I were to tell this to engrave, what it would do is it would engrave the outside edge of the text, and then come back in and engrave the inside as well, which is fine for a lot of applications. When you're trying to engrave small font on top of a small part, having those doubled lines usually just ruins the text. So what you can do is in the text, under the font, if you scroll up, you'll notice there's a bunch of fonts that have a .shx at the end of them. This is a special type of font that is created out of single vector lines rather than out of bubbles, like you would with a traditional font. So if I chose any of these at random, it's a lot harder to see what we're looking at, but it gives us a single line that the tool can then follow along to engrave. Another cool thing about text that I didn't know until recently is that you don't need to explode the text to modify or use it. So I used to think you had to explode it, which is to turn it into vector lines, to then, say, extrude it into a body. Like that. The challenge to that is then I have to go through and select each and every one of these little parts by hand, which can get a bit tricky, especially if you're wanting to go back in and modify things after the fact. But it turns out if you just have the text object and you extrude it, Fusion 360 will automatically turn it into the vector lines to use for the extrusion. The same holds true for CAM. If I give just this text object to the engraving tool or to a contour toolpath, it will automatically go through and plot out the vectors that create the edge of all this font, rather than this blurry, pixelated mess that it shows in the preview. That's why if you notice these text objects here that I was engraving, I'm still able to double click on them and change what they say. So for instance, I can change the year on this, since this will now be launched a year later, go into the manufacturer, and when I regenerate that engraving path, it will automatically update to the new wording. Alright, let's see if we got more questions. Just a reminder, guys, you can submit questions using the link that you see in the chat or the website that you see at the bottom of your screen. Can answer questions about any aspect of Fusion 360, whether it be designs, renders, manufacturing, animation, etc. Let's see what we got. Oh. Got one from Joanne, sorry if I'm pronouncing your name wrong. I'm trying to make an exploded view animation, but all the parts keep clipping through each other. Okay, that's a good question actually. Let me open up a complex multi-part assembly and let's walk through how to make better exploded views. So this is a small liquid rocket engine that I designed, and I'm planning on manufacturing sometime in the near future. Let me show all the parts. So I had used this file to make the exploded view render that I posted on Reddit last week, which looks like this. So you can see that's the same parts still laid out how they are. An exploded view like this is pretty great for when you want to show off multiple parts at the same time. But for some very complex assemblies, sometimes you want to be able to show off an entire assembly coming apart. And for that, you'd want to use an exploded view animation. So let me open up a non-exploded version of this engine. And let's go into the animation workspace. Now, Fusion 360 does automatically do explosions. You can see this auto explode all levels button up here. So if I were to click that button, rather if I was to select a bunch of components, then hit auto explode, the computer will think for a while, probably crash Fusion in the process. And essentially what it will do is it will just assign a random movement vector to each part and send them flying off in that direction. So you can see here, this is what it came up with. And for a lot of applications, this is more than enough. But if we watch this back, let's get a better view here. This is what Fusion thinks our exploded view should look like. And you know, that's pretty cool, but there's a lot of parts that fly through each other, they get stuck, they don't really end up where we want them to be. You know, this part here is randomly flying forward when the part it's actually connected to is flying backwards. So getting these done properly can be a bit difficult with the automatic tool. The best way to do it is just with the standard movement tools you would find in the animation workspace. So let's skip back to the start and let's delete all of that. So for those of you who don't know how the animation workspace works, it's essentially just a series of moving the parts, making them appear or disappear, and then moving your camera. So if I wanted to, say, zoom in on this connector at the top, what I would do is, let's say I want that zoom to take 2 seconds, so I'd skip to the 2-second mark in the timeline, and then move the camera to where I want it to be. Now if I watch that back, it automatically plots the course between where my camera started and where the camera ended, and makes it happen over that course of time. If I want it to be a more gradual movement, I can make it longer, and it will now take a nice slow panning effect. If I wanted to then look deeper into this part here, what I could do is at this point, select a part, and then show hide it, like that. Let's move that out. When you stretch the light bulb in the animation workspace, that will change how long it takes for it to appear or disappear. So if we watch back from here now, we're going to finish panning in on the part, and then it will slowly disappear. Now to make an exploded view, it's very time consuming, so we're not going to jump too much into it here. Essentially what you want to do though is choose some time out and just start moving your parts. Then choose another time out and move your parts. Then choose another time and move a part. This gives you more control over the direction that the parts will fly during the exploded view. So we watch that back now. We can see this now moving a lot slower, a lot more methodical than our auto explode. You just need to go through and repeat this for every part, which does take some time, but you get a great result at the end of it. Alright, we've been at this for about an hour now, so let's take a 5-minute break and make sure to submit some questions, and then we'll go on from there. See you all in about 5 minutes. All right, welcome back, everyone. Let's see if there's any more questions or if there's something else that we can work on. All right, so it looks like Mark is asking for help with making better renders. Okay, let's make some renders and get some practice in doing that. Let me pause my screen for a second and I'll jump into a part that we can use to make some renders. Alright, here, once it loads, is a basic retracting scribe that I designed. It has a carbide tip, and it's just a series of threaded and glued together parts to get some practice using different materials. It's just taking a minute to load. It's probably because I haven't opened it in so long. And there we go. So, as you can see, it's a series of parts. Let's take some renders of this put together and in use. So first things first, we need to go through and reassemble all the parts. So let's align, align, It's been a while since I opened this file. I forget if I had some sort of joint holding everything together. Let's see here. Yes, I do. That's the problem. Turn that. Put this in the, we'll put it halfway retracted, that's fine. Or actually, let's move it mostly retracted, like that. When I split parts apart for doing animations and renders like this, I always move them some multiple of 0.1 inch. That way with the move tool I could just slide them back to where they should be and there's no problem with alignments, they all match up perfectly. Alright, so this is a pretty simple part to take some renders of. Let's jump into the render workspace and see what we can do. So first thing we need to do is orient the camera how we want it to be. So let's say we want to get a picture of it, something like that. Let's clean up the scene settings to get the light perspective a bit better. And change the aspect ratio to 16:9 so we could use this on different websites a little bit easier. Now you'll notice everything's a little bit shiny. The previews in Fusion 360 make things look a lot shinier than they should be. I don't know why, I can't quite figure it out, but once we start the render, everything gets a lot duller, so don't worry about that. Now at this point, we could just do some touch-ups to the positioning. Something like that. Let's hide the browser. So you can see when we change the aspect ratio, it gives us these black bars on the side. What this will do is when we do an in-canvas render, or when you're setting up a real render, it takes it based on your screen location and from the center of your screen. So if we had just told it to make an in-canvas render or whatever without those bars there, we wouldn't know what the final aspect ratio would look like. This gives us some alignment when we're trying to match everything up. So you see, if I started the render like this, I wouldn't have known that this section will be cut off from the bottom of the picture. So let's position it just like that. At this point, you could use the render button to start a cloud-based render. I always like to do in-canvas renders though, since they are quicker and they give you a bit more fine-tuning over how the render looks. So to start that, you just hit the in-canvas render button and give it some time and you'll start processing. If we like what we see, what we could do is change this slider from something like excellent to infinite, and it will continue to make nicer and nicer renders, getting rid of some of this grainy look that we have towards the back of the image. Once we're happy with it, we can just hit the capture image button up here at the top, and it will save it as a regular image file to our computer. Let's say we wanted to get a slightly different angle. Maybe we wanted to get a look at it from this side instead. See, if you move it around while the render is running, Fusion will automatically restart the render every time you move. So if you want to move around and you don't want it to be messing up your computer, make sure to hit the stop render button before you do anything. Let's reposition the light slightly to get a better view over here. Something like that. And try it again. Alright, that looks pretty good. I'm happy with that. Sometimes you need to play around with the positioning of a part even more than just the rotational axis that we have for the lights. When you move the lights like that, it rotates the light source around the z-axis. If you wanted your light to move in the x or y-axis, what you need to do is actually rotate the entire part. And it looks like we're having some stream buffering issues, so I apologize to anyone who is watching at home and is having some sort of interruptions now. Hopefully that will sort itself out shortly. But yeah, that's how you make renders. It's not complex. A lot of it is just playing around with different positionings, angles, getting the lighting just right. I do strongly suggest doing your renders on a white background with no ground plane. By default, I think Fusion uses like a gray, something like that, and a ground plane. You can see the image really loses some of its luster when you do that. There we go. All right, let's see if we got more questions. All right, so Dean asks, can you use Fusion to make electronic PCBs? And yes, you can. Let me close this. And let's make a new electronics PCB to show you how that works in Fusion. So the electronics workspace is only available to some license levels right now. If you go to File, and under New Design, you'll have New Electronics Design. If you see that, then that means that you can access the electronics workspace. If not, it might not be available with your license, so you will have to check on your Fusion account specifically. Let me open up one of my previous electronics projects, and we'll take a look at that and how the electronics workspace works. So here is an example of a basic electronics project. This one is not designed very well. I know there's going to be some electrical engineers in the chat who are going to yell at me for how bad this is. But let's just go through the basic idea of how it works. So if you've never used an electronics CAD before, you start with a schematic. The schematic is just you laying out the individual parts and how they would all connect together. Normally you do this with a series of different pages and nets, but this was such a simple part, I could just do it by drawing lines connecting everything. So you can see I have the component representing the Arduino Uno that is at the heart of this project. And then each of the pins coming off it will just have a wire going to wherever it needs to go. Components like resistors can just go in line with the wire. Essentially, you're just drawing out your circuit. Like I said, normally you'd use net names to connect these, so I could just write, coming out of this pin, digital 1, and then over here I could just write digital 1, and it would automatically connect them without the need for drawing these complex lines, which is definitely needed for anything more complex than what I'm doing here. Even this is starting to get a little bit hectic. So from the sheet, you can then turn it into a PCB design. So a PCB design, this is the finished design here. What it will do is it'll place the rough silhouette and the pin locations of every part, and it will draw lines connecting where all of the connections should be. Then you have to go in using the routing tool and manually draw the lines connecting all the parts together. So you can see it will automatically create a PCB trace wherever I draw the line, and it will highlight what two pads need to be connected. So if I select something more complex like the ground, which I think should be this one. No, where's the ground? Here's the ground. There we go. So you can see the ground connection, there's obviously a lot of them. Normally you would achieve this with a ground plane where you just make the entire thing out of copper. I wanted the routing experience, so I just did it all by hand. Do you see the white line that's sort of crossing over everything right now, wherever my mouse is to wherever this point is? That's what it looks like when you haven't fully completed a net. For some reason, Fusion does not count the connection from here up through here and then to here. I know for a fact that it is actually connected because I got these boards in real life and they all tested just fine. So I'm not quite sure what that's about. You can then change the width of the trace up in the trace menu to make them thicker if you had to run more power through them. And you can define a board shape just using the board shape tools. In this case, I wanted this to be a shield for an Arduino Uno, so I traced the outline of the Uno component and put the holes in the same spot. And then I put some text on it. So the text can be seen. Some of the text here is just the text from the parts themselves. A lot of them have labels automatically generated. And you can see I put some additional text here. It's a bit tricky to see. Let me see if I can isolate that. This would be under bottom values. Yeah, there we go. So your text, you want to be in the T values or B values level of your PCB, so that when you send it to the manufacturer, they know where to put that text. I made the mistake once of putting the text on one of the trace levels without realizing it. So what they did is they engraved all of my text as if it was a wire on the board. So this view is not great and easy to see exactly what we're looking at. So what you can do is hit the View 3D PCB, and based on what you input, it will automatically generate the board. Some components will automatically have a 3D model that's accurate to how they really look, whereas others will just have a jelly bean placeholder for them. But this gives you a 3D model with full parametric control over it as if it was an actual part. So you can then take this design for this board once you have it manufactured and import it into your other CAD projects. So if I go to the full assembly for this project, you can see I was able to take this board design. It's going to update. There we go. Put the pin headers on it like you would. Find some more components to fill the rest of the slots. And then put the whole thing on an Arduino Uno. And this gave me a very realistic representation of what the part will look like. And it's a lot easier to see that text that I talked about here. So if I hide the Uno, I can flip it over. And you can see all the info on the back as well, including the automatic serial number that would be put by the manufacturer. The electronics workspace in Fusion is great for very basic parts like the shield, where we're just connecting wires together. For more complex things, you still probably should use the another bigger ECAD package like Circuit Maker, Altium, or OrCAD, since their libraries will tend to be more complete, and making new parts is a massive pain. Hopefully, though, Fusion will update with more libraries in the future, and things will get a lot easier. Let's take a look if there are any new questions. No new questions. Are there any more questions from anyone in the next few minutes? If not, we'll probably wrap it up here and call it a day. Let's just see if we get anything new. Remember, you can submit questions using the link in the chat or the website that you see at the bottom of your screen. No, all right, it doesn't look like we have many more questions, so we're going to call it there for today. I hope that some of you were able to learn something new and exciting, and I hope to see you all for our next Fusion 360 office hours. Make sure that if you have a question or any problems, you can submit it through the website, and I'll read through them and reply to them, or check out the Fusion 360 subreddit to get some other help with your projects. All right, thanks for joining me today, everyone.